Alright, when November the 10th. Alright, let's get this one going. Oh, we did it not a long time ago. Really? We just... Oh, that was yesterday. This is today. Refresh. Yep. Shortest subarray with or at least k. You're given an array nums of non-negative integers and an integer k. An array is called special if the bitwise or of all its elements is at least k. Return the length of the shortest special non-empty subarray of nums. An array is called special if the bitwise OR of all its elements. Bitwise OR of all its elements is at least k. So I return the length. So I have 1, 2, and 3. And we want the bitwise OR of everything is at least 1, 0. Or is it -1 if no such subarray exists? Hmm. Actually, the second one. A 1, 0, 1, and a 1, 0, 0. No, 1, 0, 0, 0. If we exclusive OR everybody, we get a 1, 0, 1, 1. What's that? 8 plus 4. That's 14. No. 8 plus 2. That's 11. So we need all 3 of them. And 10 is 1, 0, 1, 0, right? This is 10. Okay. So based on the k, I know the leftmost. Okay. Well, I mean, first of all, if I have a value that's bigger than k, then it's just 1, right? If I don't have a value bigger than k, if I can sort it, so now I get the biggest value, can we say that... I mean, we can also all, if we all everybody, we can get the largest value, right? If we all everybody, it's not bigger than, that's also not going to work. So if we all everybody, and it's larger than k, but none of a single number is bigger than k, then we need to start thinking. So we can go the largest. Oh, we cannot sort because it has to be subarray. Interesting. Can we just take from the start take until we hit it's larger or equal to, right? At least, yeah, larger equal to k. And then can we start shrinking? Because, we have to take all of these. But what is the operation to shrink? Um, yeah, I think we can just go and then we start shrinking. Like in this case, if all these two would be 1, 1, right? And if I want to shrink, the previous is a 1, 0. Oh, wait, hold on. Is it exclusive or? Well, I'm a 1 and you are a 0. So it's, yeah, that's the thing. Because if I have a 1, 1, then we'll get a 1, 1 as well. Then you don't know. Yeah, it's hard to shrink. What's special about bitwise or? That if it's a 0, it will remain 0, right? If it's a 1, that's the thing. We don't know who give it the 1. Hmm. Let me think. Let me think about this. Maybe. Basically, I say if I have a 1, 0, or something, or x, I get 1, 1. Can I say 1, 0? If we say and x equal to. Oh, hold a second. We can use. Wait, hold on. What do we need? Well, we want to know this x, right? We don't know what this x is. How do we know this x? Well, what if I say I AND everything? Then there will be a Y. This is like everything AND together. And, well, if these two AND, it will be 1, 0. Right? Because of this, all the zero, that means all the zeros should be where we have a value, but all the ones we don't know. It could be a 0, it could be a 1. Yeah, that's the thing, we don't know. So we cannot remove from the left. But feel like you need to know how to get rid of it. How do we get rid of it? Count. Count. Each position I count how many ones. So I will have a counter and everybody's int. So it's the counter of line 32, right? And for each number I put in, I will count. And then I'll I just count, right? So at each position, like I or it, I just do the counter. I or do the counter, and every time after I do a counter, I will go through 32, right? Go through 32, and then I'll go through 32. I go through 32, and then for a position that has a 0 count, that's a 0. If it's not a 0 count, that's a 1, right? Because it's or, it's a 1, and then I will compute the value. If it's smaller, I'll keep going, right? I'll keep going until I hit something that's bigger or equal to k. I record the value, right? I record the length, and then I start shrink, right? If it's larger than equal to, I shrink in the front. I shrink the front. So I just extend, I shrink, extend, shrink. I think this is the 2-pointer, right? Kind of 2-pointer. And then when we shrink, we just remove the count. Now we just remove the count, and every time we just recompute. Well, I think it shall be okay. Right? It shall be okay. Yeah, we just every number we add, right? And then we say while this is larger, I remove, and then eventually we'll get the count. Okay, we can use counter. We use counter to simulate or. Okay, let's try this. Counter. So basically we can say a counter 32, okay? And then we'll have a int function convert. We convert it into the int. Right? 9. What 9? It should be 0. Okay. and I say if counter dot length -1 minus I, right? Because go right to left. If it's larger than 0, so means we have a set bit, and rest all equal to 1 left shift I. Right, and I will return rest. Otherwise, not 1 left shift I. Okay. Then we'll say for int we'll have int I equal to 0, and then we say j equal to 0. J is smaller than nums dot length. J plus plus. Okay. So every time we do j, we will update counter. Okay. So say private void update. And current number. Okay, how do I update? We will go through number, right? And then nope. Let's say counter. Okay, while n is larger than 0, if n and 1 larger than is not equal to 0, larger than 0, right, then we'll say counter I plus plus. Oh, update. Boolean is remove, is add. Okay. Actually, we do int effect. Delta. Plus equal to delta. Right? And then we say I minus minus. Right? And if it's equal to 0, then there's no count. We don't add. It's only if it has, this position has a 1. Now we either add a 1, right? Oh, and need to left shift equal to 1, right? Okay, so let's update. So now for each number, what comes in, right? And I will always update. We call update counter and nums I 1, right? So we'll update it, and then we say while convert counter, which is the total, right? If this is larger than k, right? If it's larger than k, then we will do update counter nums I epsilon. This shall be a j minus 1, and then I plus plus. Right? So we'll update it, and then we wait, hold on, no. It shall be yes, if it's larger than k. Right, if it's larger than k, then we'll remove. Then what if it becomes smaller than k? Right? So basically we'll add 1. Okay, we add 1, and if it's larger than k, then we shall do something. Right? If it's larger than k, then we shall record it. Because otherwise, if it's larger than k, then yeah, we can update inside here, right? We can update inside here. Nums.length. Actually, no. Maybe we can do integer.max value, right? So while it's larger than k, they say it's at least k, right? So if it's larger or equal to k, we can say res equal to math.minimum res j minus I plus 1, right? And I remove it. Try it again. If it's logical to k, I can do it. If it's not, we jump out. Right? We jump out. So every time we just add it. If it's logical to k, we try it. Right? Yeah, if it's logical to k, then we try it. If it's logical to k, we try it. If it's smaller than k, right, we remove the last one, becomes smaller than k, then get out. So as we just run to the end, and I can return the rest. This is okay. One more. Well, we'll just run it, see how it goes. The first one. Okay, this one looks good. Now I run all of them. That is interesting. So I cannot be larger than, right? So if, well, this and I is smaller equal to j. Okay, that's also good. All right, so but we also have a scenario where it's just not possible. For example, we have, all ones, and I can do, like 10, right? So at the end, we shall say, return, hold on. We shall say return res is equal to integer dot max value. If it is, that should be -1. Otherwise, it should be res. Okay, that looks good. And then we can write it. Okay, basically what we say is 2 pointers. 2 pointer plus a sliding window. The tricky part is to enable sliding window on cumulative OR. When we remove, and here we use a counter, right? We use a counter to simulate OR, right? This way we are able to delete numbers, delete a number while keeping the cumulative OR of the remaining numbers. Or we call it ON, but technically 32N, right? Alright, let's see if this one pass. Again, run the tests, submit it, and we pass. Not too shabby either. Binary search. Has valid subarray, just go through with a current window size, just exclusive for everybody. But how do you update bit? Oh yeah, it is using update bit counts. It is update bit counts, which is exactly the same as what I was doing, right? Update bit counts. They're using the bit count to simulate. And they're using sliding window, not sliding window. Yeah, it's binary search with sliding window. See, we have the delta, the same. Bit counts, number, and delta. It's exactly the same procedure. Plus equal to delta, you see that? Yeah, we are doing the same. Sliding window, yeah. This is, I think, pretty standard sliding window, I think. Bit counts, update bit count. We have update while smaller than, which is this. And this is convert. We even use the same thing. Update, convert. I just didn't use bit counts, right? Update, convert. And I have the current length and I update it. And then Windows star plus plus, it's I. No. Yeah, I plus plus. And then Windows N plus plus is just J plus plus. Right, and the main length equals exactly. This is exactly the same. Okay, exactly the same. You have enough bitwise. You don't want to do any more bitwise. I think it's been bitwise for a while. Okay, this one's pretty good. We got the correct solution. Okay, that will be it for today. I'll see you guys tomorrow. Adios.